Welcome to the Untangling Web3 podcast. Joining us on today's show is Bowen Wang, Head of Protocol at Near One, the R&D hub driving forward the Near blockchain and ecosystem. We've invited Bowen to explore the challenge of scalability for major blockchains. This is something that stands as a banana skin to mass adoption. We want to discuss with Bowen some of the exciting developments with Near's latest upgrade, Nightshade 2.0, in the context of scalability. So let's get started. Bowen, welcome to the show.
It's great to be here. Nice to meet you, Jack and Alex.
No, thanks for your time, Bowen. I'm really intrigued to speak to a proper professional, someone who's properly deep into the weeds of this topic of scalability. You're head of protocol at Near One, so I can imagine you're uber technical, which is great. And we'll get into all the weeds of that. First and foremost, why don't we just start off by grounding ourselves in this idea of scalability? So how would you contextualize scalability for blockchains and that challenge? Because it's something a lot of people talk about it, but what does it actually mean to you?
Yeah, so it's basically the problem that we need to solve in order to get to mass adoption of blockchain, of crypto. This is because, one of the fundamental promises of blockchain is to build this global financial system, or at least be a foundation for that. And then you can build various things, applications on top of that. But this foundational layer needs to be scalable enough in order for everyone in the world, or billions of people, to use it together without having to either wait for a very long time or pay an extraordinary amount of fees to use the system.
It's like a good summary. I think when most people think of blockchain, they think of crypto. When they think of crypto, they think of digital money or electronic cash and these kind of things. And when we look at the classic examples of Bitcoin, Ethereum, and their TPS and how many transactions they can support, it's like in the single digits and double digits, right? It's up to 20, 30, these kind of things. And when you look at like the current financial systems, the Visas of the world, they're processing like 50,000 transactions per second. And it's a real kind of fundamental like problem there where we can't actually get to that mass adoption because we don't have the capacity. So why is this such a problem? When we talk about like decentralized ledger technology, why is it such a problem? How has it been such a problem so far to get this like throughput, this scalability?
Yeah, so in traditional blockchain design, how it roughly works is that there's some node that does the computation, right? Let's say you have some transactions, or let's not worry for a second about how you get the transactions and so on. But let's just say there's some transactions, right? So what the transaction is basically a kind of like instruction to do some computation. If you think about it from a technical point of view, and then there's just like a whole bunch of these things, right? And then you need to run the computation. Okay, that's fine. But like let's say you have many nodes. Let's say 1,000 nodes, or those nodes are just machines, right, in this network. And for like someone who's like completely unfamiliar with blockchain, they might think, okay, you have 1,000 machines, then they should be able to do a lot more work than what one machine could do, right? They should be able to process a lot more transactions than what one machine could process. But that's not how blockchain works. How it really works is that those 1,000 machines all do the exact same computation because they need to reach consensus on what the result of the computation is. So it doesn't really scale that way. And because of that, in this traditional like design, it is limited by what one machine could do. And it's not, I guess it's even worse, right? Because it's not just you're doing like one machine doing the computation, but you also need to spend quite some time or like quite some resources communicating with other nodes, reaching consensus through some complex algorithms, and do things to prevent malicious attacks and all of that, right? So it's really worse than what one machine could do. So that's, I think, big part of the reason why scalability is very hard for blockchains.
That's a really good way of explaining it. And I wonder if you could talk a little bit about the trilemma problem. It's something that we've touched on very briefly, but it seems extremely relevant when you're talking about blockchain technology and why it's like so far struggled with the idea of scalability. So just the three pillars of scalability, security, and decentralization, and why they're kind of opposed in some ways.
Yeah, so I think maybe the good way to think about it is still to come down to some concrete example, right? So let's say imagine you have a system that is one machine, right, doing everything. Then you can potentially make it more scalable by I don't know, throw more hardware, building this bigger machine, and so on. You can have security measures to make sure this one machine is really secure and so on. So, but then like it is not so different from any of the centralized system you have today, right? It's like Visa or whatever that you have talked about before. Now, if you want to make things decentralized, you introduce a lot more machines. Let's say now you have 1,000 machines. Now the difficulty becomes like, how do you make sure like those 1,000 machines can actually agree on what the result of the computations are and what the actual state of the blockchain is, right? So like, fundamentally what those machines trying to do collectively together is to agree on what the state of the blockchain is and continuously updating the state and always in agreement on what the state of the blockchain is. And that's where the difficulty comes in, right? Because by adding those 1,000 nodes, you're not increasing the throughput or increasing the performance scalability, and you are actually making things worse, right? You're because they need to find some way to agree with each other, and this process is actually very complex and error prone, and that's where the security concern comes in, right? So usually in blockchain, there's this thing called BFT assumption, which means that you tolerate up to 1/3 of like potentially malicious node, and this is a concept that doesn't exist in traditional centralized system, right? So in centralized system, they like machines could be faulty, but the worst you can do is to not be online and not doing the computation. But here you need to think about, okay, what if there's some guy who wants to actively sabotage the system, right? It's not just like his node is offline, but he actually is online, but he's trying to do something that to gain advantage of the system, to maybe even like steal like user funds or trying to mint money out of thin air or like things like this, right? Because it is not just a piece of infrastructure, but it also has this monetary primitive built into the system, and that is really powerful. But also it means that you really need to think very hard about how to make it secure and guard against malicious attacks.
Yeah, that's such a comprehensive way of explaining it. I think 9 times out of 10 people would struggle to give a better answer than that. And I think it's worth us just noting, these are problems that are in some way specific to blockchains, but there are analogous problems in traditional computer science, right? So if you take something like Facebook or Twitter or X, what now it's called, they have similar issues because they're operating this massive system. They have huge number of servers, huge amounts of data they have to manage, and they are operating distributed systems themselves, actually, right? So they have to deal with something called the cap theorem, consistency, availability, partition tolerance. But all of these things that you have in the kind of traditional Web2 world they all operate within a single trust boundary, right? It's still operated by Facebook, still operated by X. So now in blockchain, you have the additional complication of how do we reach consensus among untrusted parties, which is, I think, why the scalability problem in blockchain has been so much harder to solve than what we've seen there. So looking to solving the problem, can you just describe at a high level, some of the kind of major flavors of scalability solutions that we've seen out there? Because I know there are lots of competing ones, but could you give us a kind of brief overview?
Yeah. I think maybe I would like summarize it in 3 categories, right? One category is basically I would call it like throw hardware at the problem, right? So you still it's traditional blockchain design, but the idea is basically saying that there's Moore's law and hardware is growing and becoming more performant year by year. The problem to make the solution to make blockchains more scalable is to not only utilize very expensive hardware or like more expensive hardware, but actually take advantage of or like trying to squeeze everything out of hardware. That means making the computation extremely parallel within one machine, and also fully utilizing the network bandwidth of connections and trying to push as much as possible through that. So I think in some sense, that's the approach that Solana took and what they believed in. You can have more, you can basically run more and more expensive hardware and to keep up with the demand. And also they did a lot of optimization on the hardware level to fully take advantage of. It's not just you have the expensive hardware, but you actually try everything you can to take advantage of the CPUs, network bandwidth, and everything associated with that.
And Bowen, on that point, does that, in your mind, like say, reduce the idea of decentralization in a way because you say increasing the requirements of someone to participate in the network because all of a sudden, instead of running on my Raspberry Pi, I have to run it on this, incredibly powerful machine that only a few people can purchase?
I don't think it's as extreme as people put it in either direction, right? It's neither extremely centralized nor is very good for decentralization. So it is definitely not at the state where there are only a few people can buy the machine. Like I think people underappreciate the development on the hardware over the years and how cheap things have become, right? Like these days, let's say you need a machine with 128 cores, on the CPU side, and you need like 512 gigabyte of RAM, and then you need like 1 terabyte of SSD and something like this, right? It's or like and then you need like 10 gigabit of network connection. I mean, it sounds like pretty crazy, right? But I think this thing actually is not not extremely expensive to build, right? Like if you do it on the bare metal level, then like I think it costs like I don't know 500 months or maybe like 700 months, which is I wouldn't call it crazy, but at the same time it's still like not cheap in the sense that it's not something that everyone can afford, and it still like takes money and time to set up, and you need to get it on the bare metal data centers and do it on the bare metal servers instead of doing it on the cloud. So it's I think it's still limiting to some degree, but it's not as bad as what some people make it to be.
It kind of makes sense, right? Like $500, $700, that's not that much money. Not everyone in the world wants to be a validator on Solana or whatever, right? That's a very like small sect of people. But yeah, I cut you off. So you talked about the 3 different buckets and you just covered the first one about throwing hardware at the problem. What are the other two in your mind?
Yeah, so the other two all like fall into the category of like trying to scale on the kind of software design level, right? On the design of the system. So one is this homogeneous sharding approach that Near takes, right? So basically the idea is that well, the idea is not foreign, right? I think Jack already mentioned like how Facebook handles like billions of users every day. Like they don't run on a single machine, right? They have a very sharded system that runs on a cluster of many machines. The idea is that you divide the state of the network into many shards so that no single machine actually tracks all the shards or the entire state of the network. And then you like logically each shard is its own blockchain. So basically instead of having one blockchain, now you suddenly have like let's say 100 blockchains. And then your throughput is basically 100x in the ideal case. And coming back to the original analogy that I talked about when we started, so now instead of like those 1,000 machines all do the same computation, they're divided into let's say 10 different groups, and all the machines within those groups do the same computation, but between different groups they do different computation. So you scale that way. So you essentially get the throughput of 10 groups rather than, or like 10 machines rather than one machine.
Today's episode is sponsored by the VeChain Foundation.
Now, we often talk about how emerging technologies like blockchain have the potential to revolutionize sustainability, and VeChain is at the forefront of this green movement with initiatives like VBetterDAO. Let's take a closer look.
Imagine tracking small actions like recycling at low cost, making them valuable assets. These verified records build a massive collective impact, benefiting people through their own actions. Sound a bit complex, but VeChain made it fun. Explore our apps at vbetter.com.
VeChain's goal is to power a new era of sustainable solutions. So if you've got an app idea or just want to earn rewards for small, sustainable actions every day, go check out vbetterdao.com to find out more. And now, back to the show. Okay, that makes sense. So, we're here to talk about sharding, right? Because that's what you adopted Near. So should we dive into it a little bit? The idea of breaking up the network into different locations and like having people route to different parts of the blockchain when they need to. I kind of get it on, say, the Facebook level. If I'm based in, I don't know, say Europe, then I would have a Europe server that covers all my friends that I'm messaging in Europe. But how does it work on, say, a blockchain level where people are transacting across border all over the world? Like, why don't I need to have the entire history of the chain to actually support that kind of transaction?
Yeah, that's a great question. So basically, how it works is that all the user accounts are in the blockchain state, right? But instead of just having like one global state, it's actually divided into many shard states. So let's say Alec want to send me some near. So your account may be on shard 0, my account may be on shard 1. But then there is a way for us to communicate with each other, right? You can still send a transaction that goes from your account to my account, and actually, grounding that in Near's design, people don't actually even think about which shard their account is on. It's just like not something they worry about. It's what the system handles behind the scenes, and they just send this transaction, and then somehow magically it gets processed, even though the accounts can be on different shards. And how exactly that happens is quite complex, and it's basically all the thinking and design that went in the past 5-6 years.
That's a very nice way to ground it in an example, I think, because when you start talking about people's accounts being in different shards, that's when me as a technical person, my head starts to explode a little bit because I'm thinking, okay, what potentially are the problems with this, right? How do we get consistency between them and things like that? But I think that makes it a little bit clearer. What are the kind of technical challenges then to making this work? Because I know sharding has been around as an idea for a long time. People have talked about the potential sharding of Ethereum and things for years. So can you talk us through like what are the technical trade-offs and things you have to think about here? And specifically, is there anything that you're kind of sacrificing in order to get that benefit, or is this kind of a net gain to an ecosystem like a blockchain like Near?
Yeah, I can definitely talk about some of the challenges or difficulty with sharded blockchain. Sure. Right. So one, I think the first thing is security, right? I think that's a big reason why sharded blockchains are hard, right? So in the traditional blockchain, or again, unsharded blockchain, you go with this assumption of up to 1/3 malicious validators, right? And people come up with BFT consensus algorithms and so on and so forth, and all is fine. Now, in this sharded blockchain, it becomes more complex, right? So let's say you still have up to 1/3 of malicious validators, but then let's say you have 10 shards. And then you can imagine that there is some mechanism to somehow, assign, so to speak, validators to shard. But you could easily end up with in a situation where a shard has a majority of validators being malicious, right? So let's say not just over like 1/3, but could even over 2/3. And depending on how you do that, it could be that malicious validator can easily take over the shard, and then you kind of screwed, right? So this is because the reason why you're screwed is because it's not that if they take over one shard or only that shard is in trouble, like because the token, or like they could basically just do something malicious on that shard, and it actually propagates to the entire system, right? Let's say they mint 1 billion tokens, and then they send it to accounts on other shards. Now, even though other shards were never corrupted, they didn't know that that corrupted shard was corrupted. So they just like, okay, I process this incoming transaction that sends me some tokens. Okay, things move on. But those 1 billion tokens now essentially corrupt the entire system.
You've got me thinking about loads of different kind of perspectives there and points, and like we're trying to keep it somewhat high level, but you kind of already going into the realm of the more technical stuff. It's like, to keep it high level, is the main benefit here of sharding that you can have this own self-regulated shard that can achieve its own consensus in a way and be like its own separate blockchain? And then say, imagine if I separate it based on continents, which is obviously doesn't make sense, but I will, and I have this European continent that's doing all their transactions, and if it's me sending to Jack and we're both in Europe, that's fine, because I don't have to worry about things that are going on in America, for example. But then is that the main net gain there, that we can kind of self-manage ourselves until the point that I have to send something to an American shard, and then there's just that single transaction that goes between us, which is still complicated?
Yeah, so I think there are basically different designs even within sharded blockchain. So certain designs make the shard more like you explicitly have this basically they make each shard a blockchain.
Mhm.
And there are advantages and disadvantages with doing that. But basically, like if you still make the system kind of one system instead of just having like 100 separate blockchains, then the key difference is whether they share the security or not, whether
Mhm.
they share the entire, like whether the same validator set is providing security to it, right? That's why, like, even though there are like hundreds of Cosmos chains out there, they're not like the same system. They're just like different blockchains.
Mhm.
But here we actually wanted to be within the same system because it not only give rise to advantages like sheer security or like being one system, but also things like composability and that is built into the system natively, right? So in Near's design, it's not that every shard is its own separate blockchain per se. It's more like I'm trying to kind of work on the analogy that you just talked about. It's more like people you don't like, you just use the system. You don't actually worry about which continent you're on, and somehow
Yeah.
magically like the system figure out like how how it divides people into shards and then figure out all this stuff behind the scenes. Because the reason is that each like two shards on Near are pretty much like equal to each other in the sense that there's no like real difference other than the state that it holds. Like all the other aspects are the same, right? How the transactions are executed and how the runtime works and so on and so forth. So that's the homogeneous sharding that I talked about.
I mean, maybe in the analogy, I was thinking, I was going to say it's like the internet and you don't know where everything's coming from, but
Yep,
we have domain names. So
yep,
if you do know what you're
yep,
doing, then you do know. But maybe it's more like social media, right? When you're on Facebook or Twitter, you have your timeline of posts. You don't know where they're coming from. You don't know the country of origin of each person, but it's still coming, and you're not thinking about where it is. You're not thinking about which partition or shard of the kind of big set of things. So yeah, I think this is really interesting, that distinction you made. You're saying that it's sharded but is still one system, because
yep,
when I hear sharding, sometimes I think of it as, okay, is this a layer two solution? You have like second layer blockchains, but this sounds to me like it's a layer one blockchain.
yep,
So is that, maybe if we can get into the specifics of Near then, and also about Nightshade, because I know there's a very exciting upgrade to talk
yep,
about with
yep.
2.0. So yeah, how does it work, this kind of layer one sharding model for you guys?
Yeah, so that's basically the Nightshade design that we have been working on for many years. So initially we had this design of this sharded blockchain where the state and transaction processing are all sharded, but the security relies on something called fraud proofs. And you're probably familiar with that from like L2 world, where it's basically the same concept, except here it's much more complex because the consequences that you bear is much severe, because whenever this thing happens, the state of the entire blockchain, basically of all shards, simultaneously roll back together. And since early 2023, we have been working on this new design called stateless validation. That is something that also was originally proposed by Vitalik, I think back in 2017 for the Ethereum ecosystem. But for various reasons, they never got to increment that. And we actually realized that it's a really good design for sharded blockchain, even though initially it wasn't proposed to be adopted in a sharded setting. And it helps us with many different factors, including the difficulty of fraud proofs, but also like just improving the performance overall, and also adding increasing the decentralization of the network. Because as the name, so what it really means is that there are like a bunch of validators that don't really hold any state. They just like but then they can validate the blockchain, validate the state transition without having to hold any state. So this means that because they don't need to store the state locally, they can run less expensive machines. They don't really need much SSD, and it's really becomes really cheap for people to run. Yeah, so that's kind of the high level idea, and then obviously there's like a lot of complex machinery that goes in behind the scenes, like to resolve the problems. Like, well, how do you communicate between different shards? And how do you make sure the state transition is valid, and how do you resolve the security problem that I talked about before, and so on and so forth.
So you mentioned state a few times there, the state transition without knowing what the state actually is. Is this? Or can you explain that in a bit more detail? Like again, trying to keep it somewhat high level. I know these are deeply technical things, but is it like a zero knowledge proof kind of style thing? How does that work? And what are the
Yeah.
implications of that?
Yeah, so zero knowledge proof could be used for this, and then that's kind of the holy grail of proving state transition. But unfortunately, we're not there yet because the overhead of producing a zero knowledge proof is really high these days. So basically, what that means is that in order to produce a proof, the time it takes to produce a proof is something around like a few thousand x or even 10,000x compared to the native execution, right? So basically, what that means is that if it takes you 1 second to run the program, then it potentially take you like 5,000 seconds to generate the proof. So the overhead is really high, and that's why it's not practical today. But okay, that's a digression. But coming back, yeah, basically it still is kind of a proof, but it's based on this Merkle tree structure, right? So what it does is that the block producer or the chunk producer, which is a shard block, the producer not only produces a block, but it generates a thing that we call state witness. What it means is that it's basically a proof that the state associated with this block indeed belongs to the state that everyone agrees on before, right? So the how it works is that in addition to just providing you with the block, which includes like transactions and receipt, it also gives you the state that's needed to execute that block. So basically, what that means is that it includes all the pieces of state that's touched during the execution. But obviously, we need to prevent people just from providing random state, right? And then like to lead, that would lead to invalid state transition. So there is a proof that each piece of the state provided in this witness indeed belongs to the correct state. And this is a Merkle proof. And then on the receiver side, they can verify, okay, indeed this proof is valid and the state indeed belongs to the state that everyone agrees on. And then they can validate that by executing against the state witness. So that's kind of how it works.
Okay, I don't want to say got it. I want to say I think I've got it, but it's because it's very complex. But it's kind of nice to hear actually that obviously ZK stuff is kind of the holy grail, as you mentioned. But it is nice to see that these problems can be solved via the, let's say, more traditional memes. I love whenever a Merkle tree comes up. I think they're super interesting facet of crypto in general, and obviously Bitcoin. So just to kind of summarize, we're saying that we can do this kind of stateless validation because we are having this proof that kind of is related to the subset of the state that is needed for the state transition, right? And the Merkle proof is kind of an efficient way to convey that state. I think that's roughly what we're saying, which is good. I think you're nodding, so I haven't completely misconstrued it. That's great. And yeah, I think that's awesome. I think just to take that away from it, because that was something I didn't know, and I'll definitely read up a bit more on this. I'm curious. So how does this change this upgrade, Nightshade 2.0, so introducing stateless validation? What does this change for the near blockchain? You've mentioned, what is well, let's say what is the state transition for near blockchain? But you've mentioned, technically this is changing slightly how the shards can be validated and communicated. But is there any other impact on the ecosystem more generally for users, or is this all kind of just going to be if you're very, very deep into the kind of protocol level stuff? I'm interested to know.
Oh, so yeah, basically this completes our original sharding design, right? So basically it makes the system fully sharded, both state and transaction processing, and no validating node actually needs to track more than one shard in the system. And yeah, basically stateless validation is how we achieve that. And before we launched this, we were in a state where basically the state is sharded, but still the block producer needs to track all the shards, so it's not a fully sharded system. And after the Nightshade 2.0 launch, everything is fully sharded, and essentially it completed our kind of original vision for the sharding, even though through different means. And this is, I think, a huge milestone and kind of a testament to the original design that this thing can actually work. And what this means for us in the future is that we can now fully leverage the power of sharding, getting to more shards, and also improving single shard performance. We now have the foundation in place to build this truly scalable system that can serve billions of users.
Well, that's exciting. Have you started to benchmark roughly what you think this will mean in terms of like usability, in terms of like throughput? Is there like numbers to put to this on how much you think this will actually improve this? You mentioned billions of users there, which is obviously a big number.
Yeah. So I think it's actually there's two sides to the story, right? So throughput is definitely one of them, and there we actually have a goal of getting to 1 million transactions per second next year. But it's also that to serve 1 billion users, what that means is that you need to be able to handle the state growth. Meaning that it's not just about like you having to process a huge number of transactions per second, but you also need to store the state of all those billions of users. And that's, I think, a problem that's often overlooked by people when they talk about scalability. But it's actually really important, because if at some point that your node is actually struggling to store the state, then well, first thing that will happen is that it will affect throughput, because you have trouble storing the state, so you resort to means of like that are slower, and then that would affect the throughput, and then like it also means that you probably need more hardware to just keep it up, and it becomes also more expensive, and eventually this leads to it not being sustainable.
Okay. That's exciting. The idea of 1 million TPS by next year is incredibly exciting. I mean, that's going to hopefully be somewhere we can actually start to replace, the current financial systems. And when people complain that it's not there yet, like it seems like you're actually going to be there, which is really exciting. And I'm sure anyone that's like deep in the weeds of crypto and has tried to download like the entire state history and it's taken like 3 days or something like that knows some of the problems that are involved in this. That's really exciting. I guess outside of just this Nightshade 2.0 upgrade, what does the roadmap for Near look like? What are some of the other upgrades that are on your roadmap for, say, the next 5 years? You mentioned maybe the idea of ZKP and that being the holy grail. Is there other things that you are looking forward to or excited to build?
So integrating zero knowledge proof into the protocol is definitely something that we plan to do once zero knowledge proof becomes more mature, in the sense that the proof generation overhead become much smaller. And then I think another thing that we wanted to do is to basically provide even better experience for users, right? Even lower latency and so on. So today, Near blocks are pretty fast, right? Blocks produce roughly once every second, and then get finalized every 2 to 3 seconds. That's already pretty good, but I think to truly provide a seamless experience for Web2 users, or for users who are not familiar with crypto today, we want something that's even faster, right? So we're thinking about reducing block time to like 200 to 300 milliseconds, and the finality within 1 second, so that it become really a seamless experience for people building various types of applications. Because today, I think it's still like, I think depends on the type of applications you build. I think for some, maybe it's okay if people wait for a while when they need to confirm transaction, but I think for some that people really wanted to be confirmed really fast, and that's how you can build new types of application that leverage the power of blockchain and leverage the power of scalability.
Awesome. I mean, that's such an exciting outlook, and I'm really excited to see you guys go and reach that million TPS goal. That's super exciting. You mentioned applications there, and I just want to finish on this, Bowen. You're obviously super deep in the weeds, right? Head of protocol. What is it that's getting you up in the morning, right? In terms of the application of Web3, crypto, whatever you want to call it in general. What is it that you're excited to see actually happen, put in users' hands in the future? What is that for you?
Yeah, so we have this vision of building this user-owned internet, and we are also very heavily invested in AI. And I think this comes from this vision that in the future, the interface of user interaction with the internet will not be through browsers, but will be through AI agents or AI assistants. And I think we already see this trend happening, with people more and more going to ChatGPT or Perplexity when they need to search something versus going to Google and so on. And we envision this world where you do like everything, including like all the online shopping, all the trading that you do through this AI assistant. And then that's why we're building this intense layer that allow this settlement on chain, this basically open permission system where it settles on chain, but you have this solvers that give you codes off chain, right? So we imagine this like cohesive experience in the future where, let's say you want to buy a laptop, then you go to you just ask your assistant, like, can you give me some recommendations? This is what I want. And after they give you some recommendations, you choose one of them, and then this like solvers just plug into the system and just give you codes on like, hey, do you want, this is the best price I can give you, and then you choose one of them, and then it settles on chain and delivers to you some days later. So that's kind of the future that we envision. And I'm super excited about this future of user-owned AI, user-owned internet, that really transform the day-to-day experience of every single person out there.
Yeah, that's a really, really interesting topic, I think, AI agents. And yeah, I think you're hitting the nail on the head, right? That's something that, people have started talking about a lot recently in the last kind of 6 months in particular. But that missing piece of, well, what are the payment rails going to be for these agents to go and perform certain tasks, right? To go and execute things with money, with transactions. So I think that's a really good vision to be striving for. Listen, Bo, it's been such a pleasure having you on. I think we've covered a lot of ground, and I can't believe we've managed to do it, hopefully without losing the entire audience, because it's such a deep technical topic. But I think I've got a much better understanding just from having talked to you about this. So yeah, thank you so much, Bowen, for joining us. I hope you'll join us again on the show in the future. Maybe we'll get you back when you hit that 1 million TPS, and we can talk about how you got there. But yeah, all that remains to say is to our audience listening, thank you for listening, and you can join us next time to untangle a little more Web3.